Fantastic. And thank you, Grace, again for your assistance. You are greatly appreciated. All right. So hello and welcome everyone to the third edition of our thematic 2021-2022 Cosmic Exploration Speaker Series, or CESS. With this series of free public presentations, the Lunar and Planetary Institute strives to connect the public to exciting planetary and space science research. This year, the theme of our speaker series is devoted to exploring the universe with the James Webb Space Telescope. Recordings of our previous lectures are available on YouTube, and we hope that you enjoy us for the remaining talk in our series. Before we begin tonight's presentation, we have a couple of poll questions that we would like for you to respond to. Let's launch the polls, Grace. We just want to know who's in the audience tonight. So have you ever attended LPI Cosmic Exploration Speaker Series before? And second question, please rank your current knowledge of exoplanets and the techniques scientists use to study them. In 5, 4, 3, 2, 1. Thank you so much, Grace. Awesome. So we do definitely have a guest that this is their first time. So again, welcome to our speaker series. We're so happy that you're here. And please make sure that you are using the Q&A for the questions. Third question, which of these describes you? Are you a scientist, an educator, student, amateur astronomer, science enthusiast, local community member, national community member, or international community? Covering all bases, all are welcome.
And you can select more than one option. Obviously, this doesn't cover everything. We just want to get an idea of who's joining us.
Fantastic. Thank you all for your participation. It really helps us in designing and improving our program. So Dr. Kiefer will be here to introduce our speaker tonight. He is our Associate Director of the Lunar and Planetary Institute. Dr. Kiefer, take it away.
All right, well, welcome everyone. On behalf of the Lunar and Planetary Institute, I want to welcome Dr. Susan Mullally tonight. She has a PhD from the University of North Carolina. She now works at the Space Telescope Science Institute, where she's the Deputy Project Scientist for the James Webb Space Telescope, which is a short way of saying that she's way high up in an important organization. She is an expert on studies of exoplanets, which are planets around stars other than our own sun, and on studies of stellar evolution. And she is going to give us a talk titled Exploring Distant Worlds. Dr. Mullally, welcome.
Thank you very much for that kind introduction. Let me see if I can get my slides going again. I'm very excited to be here at the Lunar Planetary Institute. I have never gotten a chance to come to Houston, but I've been in Texas several times and always enjoyed my visits. All right, so that I did. So share. And then if I hit this. All right, can someone confirm that you're seeing my slides?
Looks
yes, ma'am, loud and clear.
Yes.
Wonderful, thank you. Okay, so thank you again for inviting me to tell you about NASA's next great space telescope, the James Webb Space Telescope. I'm going to cover sort of where we are in the design and the launch of this telescope, and then kind of gear it in the direction of what we're planning to learn about distant worlds, specifically planets orbiting other stars, exoplanets. So let's start this grand tour. And as I'm really happy to answer questions, and we'll probably save most of them for the end, and they'll monitor them. But if anything comes up that you feel I should answer right away, they'll feel free to interrupt me and just have me clarify, and that would be fine. All right, so what is we should start at the very beginning, because I assume not everybody actually has come knowing what's so exciting about this James Webb Space Telescope. And honestly, it's a beautiful, beautiful telescope. And so I would be remiss not to show you pictures of it being built and before it was launched. So it's a 6.5-meter space telescope that we have launched into space. Astronomers love big telescopes because it allows us to collect more light, whereas your eye only collects, half a centimeter's worth of light. That's how much light can get in. When you have a big mirror like this, you can collect more light, and as a result, we can see things that are even dimmer, things that are even farther away. And so the James Webb Space Telescope mirror is actually made up of 18 separate hexagonal mirrors that are all going to be tuned together to focus the light onto the instruments that are recording data about the universe for us. Now, the truth is, one of the things that makes Webb so special is that the plan was to launch it into space. That makes it very difficult to launch something so very big into space. Several innovative and powerful new technologies makes Webb's science goals possible. This has included specialized optics to align the mirrors, detectors that can capture and separate light from hundreds of sources at once, thermal control systems as well to make sure it cools at the right temperature and actually gets our coolest instrument down cold enough so we can actually see out into the mid-infrared. Webb is a collection of movable parts that have been designed to fold and compact into a compact formation that is considerably smaller than when it is fully deployed. And this was kind of one of the key challenges for Webb, is that we didn't just have to, we had to put the 6.5-meter telescope into space, and it had to then unfold once it got there. It's actually made not only of this 6.5-meter mirror of this 18 hexagonal pieces, it also has this huge sun shield, which you can see in the lower right-hand corner there, which is key actually for keeping the telescope extremely cool, which I'll talk about in just a few slides. But in order to achieve that, it had to be this huge tennis court size panels to block all the light from the sun. In order to keep it cool. But as you imagine, you couldn't just stick that on the top of the rocket and throw it into space. The whole thing had to fit inside the rocket. And so we actually accomplished this. I just, when I first heard about Webb, I was just coming out of graduate school, and just all the things they said they had to accomplish to make this happen just seemed unbelievable to me at the time. And so when I think back on that, and the fact that we now we have launched this space telescope is just honestly unbelievable to me in some ways, but we're kind of living the dream now, that we took that huge telescope that I showed you with those mirrors, we folded them back. They took those sun shields and folded them up and stuck them at the top of this rocket. This is the Ariane 5 rocket, and it was launched on Christmas Day last year. I hope some of you managed to wake up that morning. If you live in the United States, if you're over in Europe, at least it was closer to noon, I believe. But I was up at 5 a.m. that morning to watch this launch from my home because very few people actually got to go to Kourou, where it launched from, to see it for real. And it was a perfect, beautiful launch, as you can see here. And once it got out in space, this is an animation showing once it came out of its fairing, there was actually a camera on that last piece, which allowed it to then get this video of the solar array deploying right at the right time. And when we saw that, we knew that we could get power to the rest of the telescope to carry us through the rest of commissioning. And we knew we were off to a good start. And so I was almost in tears when I saw that happening. It was just a lovely sight to see. And it was in some ways, our last view of Webb as we sent it off into space. So after that first solar panels deployed so we could get that energy from the sun, it had to go through a series of other deployments, which are shown here. And that's when that sun shield had to pull out, and then those side mirrors had to come forward. I'm sorry, the secondary mirror had to come down, and then the rest of the mirror had to form. And that happened over that first month as we cruised out to the location where we wanted the telescope to sit, which is at a place that's called the second Lagrange point, or L2. And here's just a very not to scale schematic of this whole thing. But you can think about how, how the Earth goes around the sun. L2 is a point that's about 1.5 million kilometers away from the Earth, away from the sun. And it's a lovely location because it's farther away from us. So it's easy to block out the light of the Earth and the sun with those big sun shields. But it also keeps in step with the Earth at this location, so that it's never more than about 1.5 million kilometers away from us, which makes it easy to communicate with that telescope and to send down all the lovely data that it's going to collect. So it actually doesn't sit right at this L2 point. It actually orbits around it in about I think it's a 6-month orbit or so. And so it's not a stable orbit. So we have to keep what we call station keeping, keep it in orbit by injecting a little bit of fuel. And it's that fuel that dictates somewhat the lifetime of Webb. And it looks like, because it was such a perfect launch, we'll actually have quite a bit of fuel to keep Webb going for at least 10 years is what it's looking like. So the telescope, this is a nice little schematic of what it looks like when it's fully deployed. And essentially, as I mentioned before, it's designed so it has a cold side and it has a warm side. And on the cold side is where we do all the observing. That's where the primary mirror is. That's where the secondary mirror is. So the light comes in, bounces off that primary mirror, hits the secondary mirror, and then goes down through the center where we have a tertiary mirror that hits those instruments. And the science instruments are all held in the back there. And then there's that multi-layer sun shield, which are 5 sun shield layers that then protects it from the radiation from the sun. And if you flip it over then to the other side, that's where we have the hot side, where you have the antenna to communicate back to Earth, and that solar power array I mentioned, and also the jets used for steering and control, for instance. There's quite a temperature difference between the two sides. On that, the hottest side, we're looking at something that's like 250 degrees Fahrenheit. But on that very cool side, you're looking at something like, negative 400 degrees Fahrenheit. And one of our instruments, MIRI, is cooled even further using a cryocooler to get it down to just a few degrees above absolute zero. And all this is done so that we can actually see the universe and a part of the electromagnetic spectrum. So using light known as infrared light. Most of the images, your eyes are only sensitive to a type of light called visible light. And most astronomy images that you look at probably are showing you pictures that were taken in this sort of visible range, running, from 400 nanometers. The wavelength is about 4 nanometers out to 600 nanometers, something around there. So bluer to that, you get things like ultraviolet light, really high energy, short wavelength light. You have X-rays and gamma rays, but for Webb, we're going on the redward end. And Webb, you can see, is going even redder than what the Hubble Space Telescope did, starting at about 600 nanometers out to 28,800 nanometers, covering what we call the near and the mid infrared. If you're not familiar with infrared light, it's not too surprising. As I said, your eyes can't really see it, but it's what's given off by things that are just everything that is warm. So as you can see here is a picture of a man holding kind of like a garbage bag over his hands. But what you can see in infrared light is different than what you can see in visible light. So where that bag blocks his hands, the visible light can't get through, the infrared light can. And so you can actually see his hands through the bags. And this property of infrared light, these longer wavelengths light getting through materials so you can see what's on the inside, is one of the things we're using in astronomy to see, for instance, into the places where stars are being born through the gas and dust that they're enshrouded in. So we can see down into those stellar nurseries, for example. And so as a result, this is the whole reason why Webb was sent out to L2 to stay cool, why it was designed in the way it was to get down to really cold optics and cold instruments, so that we're not just looking at the telescope or scattered light from the Earth. We can instead see what the universe is sending us in the mid and the near infrared. The stars of this telescope are its 4 instruments that were used to actually collect the data. This image shows the footprint or the field of view of those 4 cameras against the Whirlpool galaxy, also known as M51. That just to kind of put them on scale for you, the Whirlpool galaxy is what is about 11 arc minutes across, which is about a quarter of the size of a full moon. And so there's 4 instruments. You have NIRCam, NIRSPEC, MIRI, and NIRISS. And they all, MIRI is the only one that observes at those those longest wavelengths out in the mid-infrared, and the other 3 observe in the near infrared. And the reason we have 4 instruments is it gives a lot of versatility to astronomers depending on how they want to observe. Almost all of these instruments take both imaging and what we call spectroscopy, and they do it in a variety of ways. And so, like, for instance, if you're trying to look at a field of galaxies, you might want to take spectra of each individual ones. And so as a result, you might want to do multi-object spectroscopy. And so some instruments have that ability. Sometimes you're looking at one star, and so you just want to be able to get images of one star. Or sometimes you're trying to take time series, or sometimes you actually just want to take an image. And so you want to take imaging and not spectroscopy. So astronomers have lots of different ways they like to look at the universe. And so by having this versatile suite of instruments will allow people to the most options to get the science out that they want. Now, I keep mentioning this word spectroscopy, and I introduced it without ever explaining what it was, which is poorly done on my part, but luckily I stuck this slide in. Webb is actually a spectroscopy machine. Something like 70% of the observations that people want to do with Webb involves spectroscopy. And spectroscopy is nothing to be scary. It's a big, long word, but it just means take the light and turn it into a rainbow, and then measure how bright the light is at different wavelengths, at different colors, you might say. When I say wavelengths, you can just think color. And so this is showing it in the optical, but what's great about spectroscopy is if you measure that brightness over wavelengths, you can see places where it's darker at certain colors. And we've measured gases at those same wavelengths here on Earth, and know that when you see lines like the ones shown here, that those are produced by a gas known as hydrogen. And from that, we can determine things such as the composition of the gases we're looking at, or even their temperatures or the pressures they're at. So it tells us a lot about those astronomical objects that we're looking at. So we should all be familiar with the idea of spectroscopy, because it's going to come up a lot in this talk. So that's kind of a quick rundown of what the James Webb Space Telescope is. We are still in the process of trying to commission it, which means getting those mirrors all lined up. If you've been paying attention, there is a blog site called blogs.nasa.gov/web, which will keep you up to date on where we are in the commissioning of this telescope. And just recently, just on Friday, they released some of the first bits of data, of images that we've brought down from this telescope. On the left is actually a selfie image taken with NIRCam. There's like a special mode in it that allows it to image the mirror itself. And so that's what you're seeing, are those 18 hexagonal mirrors. So we know, so as I said before, is our last image of Webb. Well, the truth is maybe this is, we now have another one of the actual mirror. And then on the right, so because the mirrors aren't aligned, when you look at one big bright star, you actually get an image for every one of those 18 segments. And so the goals over the next month or so is to actually bring all of those points of light into one point of light. So they're all focused in the same place and we get one star instead of 18 stars. And so that's what they've been working on. And so this was entirely what we expected when we looked at it. And and so they were able to identify each, so they wiggled each mirror one at a time and be able to identify which mirror segment went with each little blob of light, and then we'll eventually bring them all together and focus this telescope. And ultimately, this is all being done in order to answer some really big questions about the universe. And we've kind of grouped those questions into 4 broad areas. And Webb was kind of designed so that we could answer these questions. Everything from the early universe, where we're trying to actually measure some of the very first stars and galaxies that formed our universe. So Webb is going to look back in time and see what those galaxies are like. Then it's going to look at how galaxies evolve over time, how stars themselves populate the universe with metals. And then the topic of tonight is other worlds. What can we learn about planets orbiting other stars? So this is where I'm going to take a quick breath and make sure that there aren't desperate questions in the Q&A before I dive any farther into exoplanets. Okay, I'm going to take that pause as no, there hasn't been.
So there are some questions.
Take a quick look.
Do you want to take a couple now?
Hold on, I'm just looking at them real quick. I will keep going. I think we'll make it. I can come back to these at the end. All right, but thank you. Keep putting in your questions. I really do like answering them as best I can. All right, so these other worlds. Exoplanets. So in order for me to tell you what Webb is going to learn about exoplanets, I first need to tell you what we already know about these distant worlds. So we can understand how they're going to dig even deeper into them. And I'm focusing, when I'm going to tell you what Webb is going to learn about exoplanets, I want you to keep in mind that the way this is done is that astronomers from around the world, or actually anybody, can put in an observing proposal to Webb, say, I have a great idea of a big question I want to answer, and here's the data I need in order to answer that question. And then there's a committee of learned astronomers who go through them all and decide which programs are the most important to do, are going to teach us the most about astronomy. And that's where a lot of the programs I'm going to talk about here on how they got selected. So this actually is really a really open process that allows everyone to participate as best we can. And the next call for proposals, I believe, hasn't been announced yet, but it'll be early next year sometime, if anybody here is interested. So back onto exoplanets. So what are these distant worlds? So I think it's interesting when you start talking about exoplanets to just kind of take a step back and remember it wasn't that long ago that we were still wondering about our own place in this universe. The word planet itself means wandering star, which means there was a point where you looked up in the night sky and you saw this red dot and you saw that it moved relative to the star. And that's really all you knew about it. And from that, you had to piece together the idea that be able to predict how they would wander. And that was no easy feat. And it was only when observations with the first telescopes by Galileo, where they confirmed that these wandering stars actually were bodies and were indeed then other planets, that we were able to confirm that that Copernican notion that we had a sun at the center and that there were a series of planets going around that sun. And that gave us the idea that actually we here on Earth are just one of many planets in a common solar system. And I guess it didn't take long then, once we understood that, with Newton, that the physics that happens here on Earth also happens there out in the heavens. And that, well, if we're just one of many planets around this star, well, there's other stars out there. So maybe there are planets going around those stars. And indeed, some of the very first literature happened in like the 1600s, where people started talking about what it would be like to visit another world. And indeed, in more recent times, there's loads of science fiction out there who really ponders the idea of what it's like on different exoplanets, whether they are sandy, whether they have air that we can breathe, whether we can travel between them. Maybe they have jungles, maybe they have two suns, or maybe they would just, burn us up the moment we try to land on them. But as scientists, what we want to know is actually understand what that diversity actually looks like in the universe that we were given. And so we're going to make our first steps we're going to try to make our first steps to connect our imaginations to what those actual physical universe that we live in. So we went out so that's caused people to go out and try to find planets orbiting other stars and see if any of them are similar to our own home or any planets in our own solar system. But it was only in the early 1990s that we actually started finding a collection of these worlds. And when we did, they looked absolutely nothing like planets on our own solar system. In fact, most of the planets that we found early on were large Jupiters very close to their stars. So we called them hot Jupiters. And so I want to tell you a little bit about how we actually go about finding exoplanets, because it'll help you understand the kind of data we collect about exoplanets. So the way the very first, not the very first one, but some of the very first exoplanets were found is something called the radial velocity method. And to understand this one, you have to understand that spectroscopy again. In this case, what's happening is the planet is going around the star, but the planet actually tugs on the star as well as the star tugging on the planet. And so they actually both orbit around a common center of mass. And as a result, you get this little animation is actually slightly exaggerated, but you end up with the star moving in a small circle. And so you see you can observe the star moving towards you and away from you. You can measure that velocity, and you do that through something called the Doppler effect. And so the lines that you see in the star shift to the blue and shift to the red, depending on the velocity of that star. This technique is very good for finding massive planets close to their star. And it's very good for determining the mass of the planet. We then started finding thousands of planets in a method called the transit method. This is where a planet actually passes, it's going around the sun, it actually passes across the disk of the star. And as a result, the star itself gets slightly dimmer than it was before. And then as it passes past, it goes back to its previous brightness. This method has proven to be very useful for finding not only giant planets, but also some very small exoplanets, some that are even smaller than the Earth. It takes big surveys for it to happen, because in order for you to see this happen, the orbital inclination, the angle it's at, has to be perfectly lined up so that the planet passes between the sun and the star. Oh, sorry, the planet and the star are all lined up together. And this only happens for like 1% to 2% of exoplanets. So you have to be really lucky. And so the reason we were able to find lots of these is because we observed hundreds and thousands of stars at this point looking for this technique. And so it took actually putting space telescopes into space to be able to sit on a star and observe it all the time until a planet passes in front of it. just to give you an idea, the sun transiting the Earth is only about 12 hours. So if you were going to try to observe an Earth transiting the sun, you'd have to watch it for 1 year and you'd get one 12-hour transit in that time. So it's a very tricky observation to make, especially from the ground when there's clouds and the sun, the stars set. And so this becomes problematic. But from space, when you can sit on it for a long time, helps you make these measurements and find lots of planets with the transit method. So if you've been paying attention to these two methods, you'll notice that so far, the way you find these is not very direct. Like you are inferring a planet is there based on observations of the star itself. But there are people who are trying to directly image exoplanets. And in this case, what you're trying to do is actually get the light from the exoplanet. And it's not that exoplanets are really all that dim. There are plenty of things in the universe we have observed that are far dimmer than what an exoplanet should be, especially around a nearby star. But the problem is that the star is so bright that first you have to kind of block out the light of that star in order to see the nearby exoplanets. And this is something you may be familiar with if you've ever stood in front of car lights, for instance, on a dark night, and you can't see the car itself except for the lights until you put your hand up and you go, oh, there's the car. That's what's causing that big bright light in my face. So when you're not trying to observe the star, you're trying to block all that light out. And they use something called a coronagraph to do this. And so where that little star symbol is in here is where they block the light of the star out so that they could see the 4 exoplanets that are actually orbiting around that star. And now this doesn't cover every way people have found exoplanets. There are actually many more methods, but these are kind of the 3 main ones people think about. And what's great about this particular one is that it's good for seeing really planets that are near to us. You can see it for pretty much any inclination, and you can see giant planets this way that are far from their stars, which is, you notice the other techniques are better for finding those planets that are near to their stars. So now I want to just, because of these techniques, I wanted to just tell you a little bit about what we actually know kind of in general about exoplanets. The first thing we've established is that exoplanets indeed are extremely common. As far as we can tell, at least for planets that are closer to their star than the Earth, there's something like 1 to 3 planets small as Earth-sized or so, or Neptune-sized or smaller. There's about 1 to 3 planets for every star. And so far we have found something like 4,900 confirmed exoplanets. This is about a week old, so I wouldn't be surprised if we've already gotten closer to 5,000 by now. And because there's another thousands of planets waiting in the wings. And so you can take away from this, planets are common. Planets are more common than stars. So you have more, on average, you have 1 to 3 planets for every star that you see out there. So keep that in mind when you go out and look at all those stars out there. The other thing to note is that, at least for that close to the star, we see that small planets are more common than the big ones. And that's what this histogram on the left, I was told this is a very smart audience, so I threw in a few plots. And if you don't get anything from the plots, don't worry about it. Just move on to the next thing with me. But you can see that there's a pileup of planets, the planet radius, a smaller planet radius there on the left. So you have, for planets smaller than about the size of Neptune, so you end up with a lot more planets that just pile up. Versus the very large ones, where Jupiter is about 10 planet radii, just to give you another grounding out there. So planets are common. There are more planets than stars, and small planets are more common than big ones. The other thing we've learned is that planets come in all sorts of orientations, shapes, sizes, masses. They're extremely, maybe not, surprising. They're very diverse. The first ones we found were hot Jupiters, but we have found also hot planets, terrestrial planets that are really close, so rocky worlds that are really close to their stars. We've found planets in planetary systems where we found lots of planets in the same system, all orbiting very close to their stars. So they're compact, like you filled every orbit that you could imagine and still have them all be stably orbiting their star. We found them to be very cold ones, really far away, farther away than any planets we know in our own solar system. We have found planets orbiting 2 suns. We found lots of planets orbiting 2 suns. We found planets orbiting dead stars. We found planets orbiting young stars. So they seem to be kind of everywhere, and they also are very diverse. Some of them are puffy, some of them are rocky, some of them are water worlds. So there's a lot of diversity in the exoplanets we have found. Okay, so before I can dive into what Webb is going to teach us about it, it's very important to remember, but piecing together everything I just told you, when we discover new exoplanets, we tend to release images like this. And so this is what everybody thinks of when they think of an exoplanet. There is a world, it's near a star, it has continents, it has oceans, it has clouds. And so this is what you think we know, where in truth, it's far closer to something like this, where we know the size of the planet, we know about how long it takes to go around its star. So that's its year length, how long its year is. For some, we might know both the radius and the mass, which gives us a density of the planet, which tells us whether it's made of rock or whether it's made of all gas, for instance, so whether it's fluffy or whether it's hard. Because we know how far away from the stars, we have some idea of what temperature it's at. But honestly, like what temperature it is on this, if there is a surface on the planet, is difficult because it depends on how much atmosphere there is on that planet. And it's only for a very few and usually very large planets that we know anything about their atmospheres at all. And in those cases, we know a little bit about their temperature and a few of the materials that make up their composition. So it's the idea, the reason why people are so excited by Webb is we're going to hopefully go from what I have on the right closer to what I'm showing here on the left. Not that I think we're going to be down to charting continents by any means on an exoplanet, but we will have at least a much clearer idea of what the atmospheres are like on these planets, and maybe know more about the evolution of these exoplanets. And because there's some of the big questions that Webb is going to start to tackle as it dives into these exoplanets, is where does all this exoplanet diversity actually come from? What are those physical forces that actually drive exoplanets to look the way they do? How do they actually form, and how do they evolve? And then which of these exoplanets that we find have atmospheres, and are those atmospheres predictable, or are they just extremely random and exquisitely diverse? And then maybe if they do have atmospheres, for some of those small terrestrial ones that are kind of about the right distance from their star and seem to be at the right temperature, do any of those atmospheres look anything like an atmosphere that we're familiar with here on Earth? And does it have the things that you would expect to need, that you expect life to need? Eventually, Webb might get to answering some of that last question. So what are some of the things Webb is going to look at in its first year of observations, and what will it teach us about exoplanets? Okay, so there's two main techniques I'm going to talk about that Webb is going to do. And Webb hasn't started observing yet, so I'm just going to show you examples from other telescopes. So like, for instance, this is an image of a planetary system known as HR 8799 that has 3 planets that you can see here, B, C, and D, wonderfully named, they're all between about 5 and 10 Jupiter masses. One way Webb is going to look at exoplanets, it's going to use its abilities to do coronagraphy, which I explained before, about blocking out that central starlight in order to reveal the exoplanets that are around it. And when it does this, it'll allow it to directly get light from those exoplanets, allowing it to discover new exoplanets, as well as to be able to measure, take spectra of the exoplanets that are there. And one of the areas that Webb is going to make great headway in this is shown by this exoplanetary system, that it can do a really wonderful job for young exoplanet systems. these exoplanets you're seeing here are only about 10 to 100 million years old and are much younger than our solar system. So our solar system is about 4.5 billion years old. And so because these planets are so young, they're actually still glowing from the heat of their formation. And as a result, we can see them very, especially with Webb, we'll be able to see them very clearly. And so these planets will be observed by the James Webb Space Telescope, and they'll be able to take spectra of them and discern what their atmospheres are made of and measure things like how much carbon and water and carbon dioxide and oxygen are on there, and maybe even tease out a little bit about what it's like to be a giant planet so distant from its star. But Webb's amazing sensitivity will also allow us to look for new exoplanets around nearby stars using this technique, at least at wide orbital separations. We expect to be able to see things that are about the size of Saturn at approximately like Neptune or Pluto distances or farther out around stars, similar young stars especially. And this is an order of magnitude improvement over leading ground-based instruments doing similar studies. The other main technique that Webb is going to use to dig into exoplanets, especially to look at known exoplanet atmospheres, is something called transmission spectroscopy. And in this case, you're taking spectroscopy, but it's actually what we call time series spectroscopy, because you're going to be observing an exoplanet while it transits its star. And so what happens is you have a planet with an atmosphere transiting in front of its star, and some of the light actually, as it doesn't get blocked by the planet and it actually goes through the atmosphere of the planet before it reaches us. And so if you compare what the light you receive during transit compared to the spectra that you receive after it's transited, you can compare the two, you can see where that atmosphere has blocked, what colors of light, as I mentioned, which wavelengths of light has blocked out. And from those patterns, you can make out what materials make up the atmosphere of that planet, as well as determine things such as the temperature and pressure. Just to give you some sense of how difficult this is, one way to think about this is this image of Venus going across our own sun. And this happens every once in a while. If you ever get a chance to see this event, I highly recommend it. But if you look at this, you're seeing the disk of Venus. And if you look over there on the left, you can just make this kind of bit of glowy bit. And that's some of the light that has come from the star and is shining through us. You see how thin that little atmosphere is. And this makes it look thinner than it really is given the wavelengths, but it gives you an idea of just how, if you're trying to do like a terrestrial planet atmosphere, how little of that starlight is actually going through the atmosphere that you're trying to measure. But indeed, using the Hubble Space Telescope and certain ground-based telescopes, we've already started to measure the atmospheres of planets using this technique. And Webb, with its amazing sensitivity and its instruments that were designed to do this, we are going to be able to explore parts of its spectrum that we've never been able to do before. And as a result, especially for giant planet atmospheres, we are going to start to have really detailed studies of lots of different things in their atmospheres, telling us things like how the temperature changes as you go as you go farther into the atmosphere. This image is intended to be just sort of a quick schematic of an atmosphere, where as you go to the bottom of the graph, you're going deeper into the atmosphere of the star. But it's just to highlight some of the things that we should be able to measure using transmission spectroscopy, especially when you go out into the infrared, you can measure things such as the water, the carbon monoxide, carbon dioxide, methane. But you also be able to see, are there clouds and hazes on these exoplanets? You can understand if some of the atmosphere itself, especially for these planets that are very close to their stars and the atmospheres are all heated up, is there actually atmospheric escape happening on these planets? And then we can start to piece together maybe some of the history of this exoplanet and what physical things it has undergone during its lifetime. One way that people are talking about doing this is by measuring the carbon and oxygen content within the atmosphere by looking at the water and the carbon dioxide and such. And from the ratio of the carbon to the oxygen and potentially even to the nitrogen, you can infer where that planet formed, because you expect there to be some gradation in the carbon to oxygen ratio, depending on whether it formed far away from the star or nearby. And that happens because if you, so as a result, Webb is going to teach us something about planetary formation in a few ways. If you think about how a planet forms, actually planets form in these flat spinning disks, is our understanding. So after the star collapses, you get this large, big disk, and this is kind of a cutaway of that. And if you can imagine, close to the star is actually very hot, and so you have just a hydrogen gas envelope, and you have those rocky planetesimals will form out of the rocks that are there. But beyond something we can call the snow line or the frost line, where you're far enough away from the star that things like water freezes out, or even farther away where carbon dioxide freezes out, you actually are forming planets out of not just the rocks, but also the ices that are around those rocks. You have more materials to accrete to form large planets. And it's part of the reason why we believe we have Jupiter formed right outside this frost line. And why you have big planets out there. But one of the predictions from this is that we expect that carbon-oxygen ratio to be different farther away from the star than close into the star. Since I'm talking about planetary formation, Webb is actually going to also look at some of these planet-forming disks themselves. These are disks that were found by a ground-based telescope, a microwave telescope known as ALMA. Each of these disks are individual planet-forming disks that are going out about the size of them is about 1,000 times bigger than the distance between the sun and the Earth. So 1,000 astronomical units, if you know that term. And you can see in as close as about the distance from the sun to Saturn. So you get these amazing disks, and you see those places where you see where there's rings. And we think that's happening because new planets have just started to form between those rings. And so Webb is actually going to look to see if they can find planets in these planet-forming disks that we have found. It's also going to try to study the ices that are in these disks that are forming planets, and to be able to help us confirm what's happening, where we find certain ices of different materials, so we can even better understand things like how terrestrial planets form separate from how the giant planets form. And doing all of this, especially out in the mid-infrared, using that instrument called the MIRI that I was telling you about before. So besides planetary formation, Webb is also going to start to look a little bit about what happens to planets after their stars die. So to understand that, I put in this little graph about stellar evolution, and the bottom part tells you, the way people think about big stars. They die in a big supernova at the end of the black hole. In that case, I'm not talking about that in this case. Instead, you have a star a bit like our sun, and eventually it runs out of hydrogen, and it turns into a big puffy red giant star. And at that point, we think it's probably swallowed up out through Venus, maybe out through Earth. So goodbye those inner planets. It eventually sloughs off its outer layer, leaving behind a core, the inner core of the star, something called a white dwarf, which is actually only about the size of the Earth and is extremely dense. It's made of mostly carbon and oxygen. A teaspoon of it weighs about as much as an elephant. So if you can imagine this really dense, hot material known as a white dwarf. But what happens to those outer planets after you form that white dwarf? Do they get ejected from the system? Or maybe, as some theories say, they just move outward, and we should be able to find them there. Well, given that story I just told you, maybe a bit surprising when I tell you that the very first planet found around a white dwarf is actually just basically skimming, is a giant planet found very close to the white dwarf itself. And it was found by using a transit method. And so Webb is actually going to try to study the atmosphere of this planet. What's great about this is it's a really old planet that we're able to study its atmosphere. It's actually really a cool giant planet, is really more the point, because the light from the white dwarf is from such a small ball, even though the star itself is relatively hot. You don't have to get too far away for the environment to become somewhat cool. So this is actually one of the coolest planets we get to study with transmission spectroscopy. In another study, that we're actually going to look for some of those planets that moved outward, or let's look to see if we can find them around some of these white dwarfs. And we can be able to find planets as small as potentially the size of Jupiter out around, this is that orbital separation. 1 AU is the separation from the sun to the Earth again. So 10 AU is approximately Saturn distances. So we should be able to find any planets that are around these white dwarfs down to about the size of Jupiter, and directly image them if they are farther away than approximately Saturn is from our own sun. So soon we might know far more about planets around white dwarf stars by the end of the first year of observations with Webb. Okay, so I've been telling you mostly about giant planets so far. I want to take a moment and tell you about small planets. As I see, I maybe need to speed things up here just a little bit to leave time for questions. So Webb is going to explore diversity of planets, and so far it's been difficult to measure the atmospheres of the smaller ones, those that are Neptune size down to about Earth size. And the reason the first exoplanets, small terrestrial ones that we're going to observe with Webb are the first ones are actually going to be around very small stars. And the reason we're going to do that is that you kind of get an advantage by looking around small stars. If you can imagine that transit method, if you go around a big star, the amount of light you block is not very much. But if you're going around a small star, you block relatively more light and you get these deeper transits. And so as a result, more of the light that you see, a larger fraction of the light that you see actually gets blocked, or for studying the atmospheres, a larger fraction of the light goes through the atmosphere. And so you get more signal. And the other advantage is it allows us to actually look at planets that are not too hot and not too cold, that are closer to their star. So imagine a cool star. This is actually just talking about how hot the environment is around a star, and if you have a big hot star in the middle of that, to get to a temperate zone, or what we call a habitable zone, where you could have liquid water on the surface, you have to be pretty far away. But if you get to a smaller star, it's a smaller fire, so you're going to come closer in order to get to the same temperature. And so as a result, you get more transits. You can have that orbital period only being 10 days or 20 days, and you get more transits, so it becomes easier to see it in transit without having to wait a whole year to have something that's in this temperate zone. And so one of our favorite systems that's going to be observed by the Webb Space Telescope is the TRAPPIST-1 system around its what we call this small M dwarf star. It's only 39 light years away and has 7 exoplanets in the system. And all of those exoplanets are in orbits that are closer to the star than Mercury even is in ours. What's great about having it has 7 planets that are all like 2 times the size of the Earth and smaller. And we're going to see if those planets have atmospheres at all, and start to look as whether or not we can characterize what those atmospheres are like. And then we can start to compare them with each other, because we know that they all formed in the same planetary system. So if it has an atmosphere, we can look for signs of things like oxygen or ozone, or materials that we might be more familiar to our own life on Earth. And depending on what we see there, or how many clouds there are that get in our way, we might be able to really determine, for instance, whether they have clear atmospheres or anything that's similar to things that we have in our own atmosphere. and versus maybe they have atmospheres that are more like Venus or things that are more like Mars. So within those first year's observations, we should be able to tell the difference between some basic properties of what these atmospheres on these terrestrial planets are like. We're also going to look at some more exotic worlds. This is an artist rendition of a world known as K2-141b. This planet is only in a 0.3 day a year orbit around its star. It's only about 1.5 Earth radii, and it's so close to its star that it's actually tidally locked. So the same side is always pointing to the same part of the sun, but it's so close that it's roasting hot. And so basically we expect there to be no real atmosphere, but it might have an atmosphere made up of vaporized rock. And since it's tidally locked, 1/2 of the planet is being much hotter than the other, and that might stir up winds. And so as material moves from that hot day side over to the night side, it's possible that it might start raining lava. And with Webb, we should be able to detect evidence of that. And so we're not only just doing these temperate worlds in the hopes that someday we can find things in the atmosphere that are reminiscent of things we know people that life likes, but we're also looking at the full diversity of planets out there and starting to understand these lava worlds that we have found. Okay, so that was a pretty quick tour of some of the questions that Webb is going to tackle in its first year. I hope I gave you some impressions that there's a large diversity of different types of exoplanets and science questions that Webb is going to try to answer in that first year, whether it be looking at terrestrial lava worlds or temperate, potentially habitable worlds, or whether it's looking at young, newly born planets, or what happens to planets after their stars die and turn into white dwarf stars. And so with that, I hope I left a little bit of time to answer some questions. So thank you.
Fantastic, and you did a phenomenal job. So thank you for this incredible presentation. And so we do have a few questions in the chat box, and I want to go ahead, Grace.
Just want to say, since we're at the top of the hour, if people need to run, we'll go ahead and do our evaluation questions, and we'll remind you that once you leave this webinar, you'll be directed to a survey, and we'd love your feedback. But Dr. Mullally has kindly agreed to stay on for an extra 10 to 15 minutes to take questions. So if you're able to stay on, we're going to keep the webinar running. We're going to keep live on YouTube. So please stick around. We're going to do Q&A. But before we do, we'll just kind of get our poll questions out of the way, and yeah, we'll let Dr. Mullally get a sip of water. So I'm going to just launch these real quick. So there are 3 questions here. We just want to know if this program that you attended tonight has affected your interest and awareness in the James Webb mission, how likely you are to attend another one of our public lectures, and we have more coming up that will address other topics to do with the James Webb. And then finally, if you're interested in receiving notifications from the LPI about our upcoming events or other resources, you can let us know in this poll, and we can do some work to help you get subscribed. So we'll just give you a couple more seconds to answer these questions, and then we're going to get right back to the Q&A.
And if anybody can't stick around, I'm putting my Twitter handle in there in case you want to find me on Twitter later and ask questions. And I will do my best. I'm not there every day, but I am around occasionally.
All right, so I'm going to stop the poll. Thank you all for participating, and keep putting your questions into the Q&A, and we'll just take it away. Sherelle?
Fantastic. Well, I want to let you know, if you haven't already, cruised the Q&A in the chat box directly from Adrian and Paul. They thank you so much for your thorough presentation. So I definitely wanted to start off with those, so that incredible and positive feedback. So thank you, Paul and Adrian and Jim for being in our audience tonight. So we're going to go ahead with the first poll question. The first Q&A question that comes from Adrian. When will James Webb start to study exoplanets?
So we haven't put together the real plan for what order we're going to observe things in yet. I saw one of the other questions here is what percentage of time is going towards exoplanets, and it's something about 25% of the observing time is going towards exoplanets or disks or things around stars in that sense. And so, it's careful, like we have all these observations, we want to use the time that Webb has most efficiently. And so we're working to make sure we can slot them in as best as possible when they're observable. I didn't go into what Webb could observe at any one time, but it's, they can't look anywhere at any one time. So there's certain windows at which we can observe certain objects. And so for those transiting ones, it's really tricky sometimes because they only transit at particular times. So they have very narrow windows for when we actually want to observe them. So I don't know when the first one is going to be observed, but I expect there to be a few observed this summer, starting in July and August.
Awesome. Thank you for that. And then our next question comes from Robin. What is the star tracker and what does it do?
Okay, I'll give you a basic sense of a star tracker. As you can imagine, Webb needs to know where it's pointing. So it has essentially a little camera to say, hey, I found a star, and I will stay locked on that star. And so it knows where it is. I wish I could give you a more concise and more detailed answer than that, but that's kind of the basic idea. And I don't want to start leading you in the wrong direction by going into more detail.
Absolutely. Well, all we ask if you can answer to the best of your knowledge. So that's quite all right. Our next question comes from Jim. He said, what celestial objects cannot be observed by the James Webb Telescope?
Basically, Webb can observe everything except for things that are interior to it in the orbit around the sun. So it can't observe the Earth, Venus, Mercury, the sun, because it can't point in that direction. But anything that's outward, it can. So everything in the outer solar system and everything out beyond the solar system.
And it's farther away than our moon, right?
Yes. Quite a bit farther away than the moon.
So it can't
observe the moon either.
Awesome. And so will the telescope be able or will be studying M51?
I don't know. I assume it is because a lot, but I would have to go look that up. I'm sorry. I just don't know. I can tell you, though, that if you are curious, if you really want to know the answer to these, there is a place where we've listed all the accepted proposals, and you can go hunt through them and see if you can find some of your favorite objects. If you go to jwst.stsci.edu and follow the accepted proposals, it'll be a bit of digging because it's not necessarily listed exactly as you might be looking, but if you look under galaxies, you can go see if M51's in there.
That's definitely a great resource because we have a number of comments that are asking about what exactly it is observing. So thank you for that resource. And so I want to switch over to, go ahead.
No, I was going to say, once we really are observing, we're hoping to give you a sense of like what it's planning to observe week by week once we know that, but we're still working that.
Thank you. And so here's a question from YouTube. It asks, how long do telescopes look at the same star on average?
It just depends on the science that they're trying to get out of that star and whether they're splitting the light up into taking spectroscopy of the light, in which case you probably have to look at it longer than if you're trying to just measure broadband colors of the light, in which case you gather more light more quickly that way. So it just depends on the science you're trying to do. Unfortunately, I don't have a clean answer for that.
Sure, no, that's great. And Robin asks, given that Webb is orbiting, how does it stay focused on its selected target?
So how can I answer that? So partly those star trackers we were talking about as gyroscopes to make sure that it can stay pointed and stay locked. There's something called guiding that we do. And so again, once you get a star and you can keep it just precisely in its field of view, you can say, okay, I'm locked on. And if I ever start to drift, I can move just a little bit to keep it locked on. And so as a result, it can stay perfectly fixed, pointed at a particular star.
Okay, so guiding, that's great.
And I
Jim
guess you'd want
asks,
to, oh,
go
sorry,
ahead,
Sean.
Jim.
I guess you'd want to make sure that you're only ever observing things for a period of time where they're not going to go around, you're not going to go around the sun and they'll be on the other side, right? Like,
Well, you're never going to observe
be...
anything that long. There is an upper limit to how long we can observe one particular object, because at some point we just can't hold that for so long. And it's, I forget, it's something like 20 hours or something. So we're never going to observe the same thing for a whole year or 6 months or something. Yeah.
Okay, thank you.
So Jim asks, what aspect of the universe will the telescope allow us to observe that Hubble cannot?
Well, there are many aspects of the universe that it can't. So let me highlight a few.
Sure.
One, Webb is going to be able to see farther back in time than Webb ever did. You know, that Hubble deep field that that Hubble is really famous for. They're going to do similar observations with Webb, but because we have a bigger mirror and we're observing in the infrared, we should be able to see galaxies that are even farther away, even farther back in time, to when the universe was just waking up and we just created the very first galaxies and stars. So Webb should be able to do that. As I'm explained in this talk, Webb will, because we're out in the infrared, we're going to be able to see materials in exoplanet atmospheres that you can't see using Hubble. We'll also be able to see interstellar nurseries because we can see through gas and dust in the mid and near infrared. And in fact, we can also measure that gas and dust, the cooler gas and dust, using the mid-infrared. So yeah, there's lots of the universe that you can't really explore with optical light that we will be able to explore with this infrared light that we're using, that Webb is looking at.
Yeah, that is amazing. Mark asks, is there any contingency for if for some reason not all the mirrors can be fully brought into alignment to allow it to complete its mission?
So yeah, any mirror that we can't use, we can work around it at this point. Like we should be able to still observe, we just won't get quite as much light, or we won't be as focused as we might like to be. It just depends on, you know, what's wrong with it or what we can't do, right? So yeah, as long as we have at least one of those mirrors sending light to our detectors, we can do some astronomy. But at this point, we're looking pretty good that I'm not particularly worried about that at this point. But we'll see.
Yeah.
We're not done commissioning yet, so I shouldn't say such things. That selfie convinced me.
Well, Paul asked about the curvature of the mirror. So he said, are the mirrors segmented curved or segment curved so that the symbol mirror is one uniform curvature?
So yeah, they're curved, and you can adjust their position and a bit their curvature so that you get one curved mirror in the end.
Fantastic. And Adrian had a follow-up question. Is there a catalog system for classifying exoplanets like in the fictional world of Star Trek?
That's a great question. I love that. I wish we knew enough about the atmospheres of any exoplanets that I felt that we could give them classifications. This is absolutely the thing people want to be able to do. They want to be able to take atmospheres and categorize them and classify them, and that's exactly what they want to do. And so hopefully after 10 years of Webb observations for maybe 50 to 100 exoplanets, maybe we'll have that picture of how we can easily group and classify exoplanet atmospheres. So not yet. Soon. Maybe. Hopefully.
Chris asks, what will happen to Webb telescope after it runs out of fuel to power its L2 orbit in approximately 10 years?
I have not looked into the decommissioning plan for Webb, but when we run out of fuel, we can't maintain our orbit. And so there is a plan, and I'm sorry I didn't look that up before this talk.
No worries at all. No worries at all. That could be your next talk.
I will go look that up.
Right. The next question comes from Janice. Does the whole spacecraft move to aim the telescope, and how fast does it flew?
So there's kind of two ways we can aim. Yes, the whole spacecraft does have to what we call slew to the correct position. There's also a fine steering mirror inside to kind of that will put the right instrument in the right place as well. So you're observing just the right position, that's just the right location as well. So there's a bit of both going on.
And here's a question from Sahar. So what the first images will be of its sensitive information? And they ask, why is that? The first images to come through, is that classified as sensitive information?
They haven't released which objects we're going to look at first, and it's partly that they're working it out, and it's partly that I want to make a big splash.
Sure.
So that's like the main reason why.
Okay, well, awesome. That's totally understandable. And a question from Todd says, when can we expect the James Webb Ultra Deep Field to be released? And is it in the first 6 months of observations?
I don't have a clean answer for that. There's definitely programs that are going to work in that direction that will be observed in the first year. And there's even some observations along those lines that are guaranteed to happen in the first 5 months. So keep your eye out for it. It's one of the main reasons Webb was launched. It's the kind of thing that it will get better and better with time. So, you'll get your first results in those first 5 months, and then they'll find even cooler things, keep going forward.
Yes. And speaking of that, Jim also asks, what wasn't James Webb not designed for that you are planning other missions to observe? And obviously it's not for observing our system, but other types of radiation or lack of.
Let's see if I can rethink that question. So certainly, I mean, each telescope that like NASA has launched, or even that we've built, has its own unique capabilities and can observe different things. So for instance, there are flares that go off, or high energetic events such as supernova and things that primarily produce energy out in very high energy wavelengths. And so for there, you need telescopes that observe in the X-ray or the gamma ray end of the electromagnetic spectrum. So it's good for that. Webb, the other thing that some telescopes do that Webb doesn't do is take large surveys, right? Where you observe a lot of things in very much the same way, and then you dig through that data looking for particular things. And Webb is more of a point and really stare deeply at particular objects you're interested in. Though honestly, because it's looking back at these galaxies that formed long ago, in that case, they're actually getting a huge survey of really young galaxies, but that's because they're so far away, they're all close together, and you can see a whole cluster of them at once. So it does do some surveys, but other things like the TESS telescope that's up right now is doing a survey of all nearby bright stars in a particular way, and Webb was not designed to do that. So that's why we have lots of different telescopes. We need them to be able to accomplish our science. They all look at the universe in a new and interesting way.
Sure. Well, then that means that you just probably already answered this question from Glenn. It says, is there an opportunity for an emergency observation for, say, another extrasolar asteroid or comet?
Oh, yes, there is the possibility of saying this is a really interesting thing, and I need to commandeer there are ways to make that happen. Yes, and indeed that's a great example. We are hoping that we'll have another planetary extrasolar body come through our planetary system again. So Webb has the ability to take those kind of observations for us.
Awesome. Thank you for that. And I also wanted to make sure that we were pulling our questions from YouTube. Our other partner, Andy, has put some of them in the chat box. And I am looking. Go ahead, Grace.
I believe the questions from YouTube have already been answered.
All right, very good.
Yeah. So we're doing good. There was a question earlier in the chat that asked, from Terry, will we see visual pictures like we did from Hubble?
Well, you will see pictures. I'm not sure what you mean by visual pictures. Yes, they will be translated to the point where you can see them with your eyes. We're not just going to show you black. See, look, infrared radiation. You can't see. Sorry, I'm getting a bit punchy apparently at 9:15 at night. But yeah, no. So what will happen is Webb is going to take some amazing, amazing pictures. I know I spent a lot of time talking about spectroscopy, but it also does an amazing job with imaging as well. And so we'll observe things with different colors and but there'll be infrared colors, and we'll combine them and translate them then into optical light that you can see. And so you'll have to understand that that's what happened. But you'll see the universe in ways that you didn't see before.
Awesome. I think people are just so excited for the types of images that Hubble released that were just gorgeous, and we want more. We had another question from earlier on in the chat that was asking about whether the James Webb will be able to observe the cosmic microwave background.
No, because that's in the microwave. It can't quite look all the way back to the cosmic microwave background. After the cosmic microwave background, then eventually we ended up with the first stars, and that's the kind of as far back that Webb can see. We're hoping for those first stars and galaxies. That will be kind of at the edge.
All right, and we have another question from Norbert asks, does the TRAPPIST-1 system have the greatest potential for finding life?
So there's a lot of systems out there that we have found around M-dwarf stars now who live in that habitable zone, that temperate kind of distance away from their stars. Whether the TRAPPIST systems are the most likely, they're a great system for understanding. You want to compare planetary systems. You want to have 3 planets all in that same star, and they're really bright. So it's a really promising system. Webb isn't. I do not believe Webb is going to actually find life on one of these planets. What it will show us is whether these atmospheres have materials that you associate with life, right? Like whether there's water and methane and ozone, things that we're familiar with here on Earth, and whether that atmosphere is anything like something we might that we have here on Earth, which is the only place we know life exists. So it's a very limited sense of what life needs to be. I'm not a biologist, so I can't really go into that any more detail, but we don't fully understand where the full extent of what life can withstand and whether water is required or not. I've heard different theories on this. So anyhow, I don't think Webb will find life, but we might find evidence of atmospheres that don't seem so harsh as some of the other worlds we've found so far.
Fantastic, fantastic. So, Grace, do you have any more questions that we can ask Dr. Mullally at this time before we close out our program?
We've got a few more in the Q&A. Does Webb have a reasonable chance of detecting a biosignature? I guess this is sort of what we already addressed. Or will we need to wait for a larger aperture?
LUVOIR.
LUVOIR, there you go. I was going to say, I'm going to mess that one up.
I believe we're going to be waiting for LUVOIR before we find true biosignatures. I hope Webb proves me wrong, but that's my understanding of what I think we'll accomplish.
Could you tell me what a LUVOIR is?
Oh, it's the proposed next ginormous telescope that we would like to send into space. So, the decadal survey where astronomers got together and said, what would we really like to do in the future? And one of the missions that was proposed was called LUVOIR.
I see. Okay,
so it's a big.
We just got Webb off the ground, and we're on to the next one.
Well, Webb was first proposed before we got Hubble off the ground. So this is how the science is done.
There you go. All right, so then there's one last question. Oh, a new one just came in, but the previous question was basically asking about, do you know who decided the criteria or what the criteria was for accepting proposals in order to get time on the James Webb?
Yeah, so as I said, it's a committee of people who decide who gets time. So astronomers write proposals and they put their best case forward that they can make the measurement that they wanted to using the Webb Space Telescope and what science they'll accomplish by doing so. A group of, like 6 to 10, depends, people sit down and read all these proposals and discuss them and choose those that they think have the best chance of producing the best science. And this is all done anonymously, so nobody knows who wrote which proposal. And we don't know who reviewed them either. So it's a dual anonymous program at this point. So it's really just based entirely on the science that will be accomplished.
Well, awesome. Well, maybe that's best. That's best that no one knows, right? And so a question from Glenn says, are there oxygen lines in the near or mid infrastructure good tracer or life? Good tracer of life? No. Is it not a good tracer of life?
So if we find oxygen, it doesn't necessarily mean that there is life there. I'm not an astrobiologist, so I can't give you a very detailed answer on this, but my understanding is that any one thing is difficult to trace to there is microbial life sitting there on that planet. And so you have to really understand lots of different things about that atmosphere in order to make a claim that you actually have proven that there is life there. So it'll be a difficult measurement to make, and then to prove that that is the only thing that life is the only thing that could produce what you're seeing.
Sure, there's always high engagement around the question, right, of life. Is there life?
I actually have a good follow-up question from a viewer on YouTube who is asking, what would we do if we found a planet that did have all of the signatures of life?
Oh, I don't know.
Get really excited.
Get really excited.
Yes.
Everyone. I mean, I expect it will happen slowly because that's the way science goes. Someone will present their evidence. Other scientists will come around and say, are you really sure? Let's take some more measurements, and they'll prove that those measurements are real. And so over many years, will we come to the conclusion that that must be what it is. And so that's part of the scientific process. And so, we love this idea of the aha moment, and those do happen, but it's then through rigorous testing that we reach our final conclusions. And so, you can't do science, unfortunately, by reading the New York Times and the headlines that come out. And so it looks like we're backtracking at times, and we're not really, because, people are saying, it was a good idea. We're a pretty good idea. This is what's happening. And other people come back and find holes in their arguments. And that's how it all progresses forward. We then get new measurements and we get closer to the truth.
Right. And we have another question from YouTube says, will James Webb help us better understand dark matter or dark energy?
There are programs that will help us better understand the expansion of the universe, and as a result, our understanding of dark matter and dark energy. Essentially, I wonder if I can summarize that quickly. They're going to better be able to help us figure out the distances to particular galaxies, which, as a result, that will tell us what that rate of the expansion of the universe is, which then in turn tells us more about the presence of dark energy and dark matter in our own universe. So maybe not directly, but it does have some indirect programs.
Fantastic. Well, Dr. Mullally, that concludes our Q&A. We have completed all of the questions. Thank you, audience, so much for the questions that you submitted. They were fantastic. We are getting a lot of thank you, Dr. Mullally, for your presentation. We want to say thank you again for your presentation, and thank you so much, audience, for being here on this Thursday night with us. Would you please join us for our next series? Stay tuned with our newsletter as well as the social media pages for the next one that's coming up. We thank you so much for your time tonight. Also wanted to thank Dr. Kiefer, our Associate Director for the Lunar and Planetary Institute, for our introduction and for being here to support us. Thank you again so much. Grace for your support, Andy for your support. Everyone have a good night, and we will